Hello ladies and gentlemen, and welcome to Mr. Saucedo's YouTube videos. Today we're going to be talking about mole-to-mole and mole-to-mass conversions, the two simplest ways of converting between things. So make sure that you are following along in your note packets, then if you have any questions, you ask tomorrow. So let's talk about the simplest method of using stoichiometry. We've spent a little bit of time defining that and kind of talking about it, but we haven't actually used it yet. So here is the simplest form of stoichiometry. It is a comparison between the number of moles of a given substance and the number of moles of another substance. Okay, we call that a mole-to-mole calculation. So how are we going to be representing that? Well, in our class, we have Marvin the mole as our mascot, and so Marvin to Marvin calculations. Whenever you see a picture of Marvin and then another picture of Marvin next to him, that's going to be a mole-to-mole calculation. Now, something that's not even in your notes, but you might want to write it down anyway, is these are called one-step conversions because it only takes one step to go from moles of one thing to moles of something else. And the reason why it only takes one step is because all you need to know is the mole ratio in your balanced equation in order to do these problems. So how do these work? All right. Here's an actual example. Pretend you have the balanced equation below. How many moles of water would be produced by burning 25 moles of C3H8 in excess oxygen? Okay, and this is the way that all of these problems kind of look. So what you see here is the first question that you'll be looking at whenever we do any stoichiometry problem. What is the mole ratio between these amounts? Okay, so let's take a look at the problem, and I'm going to go through all of the steps that I go through when I'm trying to solve a problem. Pretend you have the balanced equation below. How many moles of water would you produce? So how many moles of water? That's what I'm being asked for. If I burn 25 moles of C3H8, this is what I'm given. Okay, two things. I'm given this piece of information. I want to know that piece of information. Now, how am I going to do that? The very first sort of concept you're going to be going for every time you do a stoichiometry problem is, what does my balanced equation say? So what is the mole ratio? Okay, this question is only here because it is, this question, by the way, is what I'm referring to. This little follow-up question about mole ratios will be the very first question that you should ask yourself kind of every time we do this, is what is my relationship between what I want to know and what I am given? Okay, what is my mole ratio between H2O, which is what I want to know, and C3H8, what is given to me? So if I take a look at that problem, I have a 4-to-1 ratio. 4 here, imaginary 1 in front of my C3H8. So 4-to-1 ratio. Why is that important? Well, when I'm doing my conversion, I'm going to need to use that piece of information at some point. Okay, so how do I solve this problem? You always write what you are given at the very top of your conversion factor box. So that's why we have this little conversion factor box here. So 25 moles of C3H8. So again, you always write what you're given at the top. Now, I'm going to be multiplying by a conversion factor. That conversion factor is going to be my mole ratio, and my mole ratio is a 4-to-1 ratio. So for completion purposes, I'm going to write down what these things are moles of, and it'll make a little bit more sense when we do more complicated things. So I have 1 mole, and that is of C3H8 in my balanced equation. I have 4 moles of water in my balanced equation. All right, so why did I set it up like this? I want my moles of C3H8 to cancel, moles of C3H8 to cancel. So it will take me 100 moles of H2O. And now think about this. It makes sense. If I start with 25 moles of this, in my balanced equation, I have 4 times that amount of H2O. So I will have 100 moles of H2O. That is how we do mole-to-mole calculations. Let's try a second one. So pretend you have the balanced equation below. How many moles of AlCl3 would you need to make 33 moles of KCl? All right, so let's go through my process. What am I asking for how many moles of AlCl3? What am I given? 33 moles of KCl. Now my follow-up question, what is the mole ratio between AlCl3, what I want to know, and KCl, what I'm given? Again, this question will never really be there for you to actually fill in, but it should be one of the first things you think about. What is my mole ratio? How do I connect what I want and what I am given? Okay, so what is my ratio between AlCl3, according to my balanced equation, and KCl? So if I look at that, I have a 2 to 6 ratio. 2 to 6. If you wanted to simplify that down, you could have said 1 to 3. Either way, you'll get the same answer. So it doesn't matter which one you do. But notice I have a 2 here, 2 here, 6 there. That's where those numbers came from. All right, so how am I going to set this up? Well, what I'm given always goes in the top. So I'm given 33 moles, and again, I'm going to write KCl for completion purposes. Next up, I need my balanced equation, and I have my mole ratio. So 2 to 6, that was my ratio. So again, for completion purposes, moles of KCl, moles of AlCl3. Why did I set this up this way? I want moles of KCl to cancel with moles of KCl. So let's do this in our calculators. Or actually, you don't even need a calculator. 33 times 2 divided by 6 is 11. So I have 11 moles of AlCl3. Again, look at your ratio and look at your equation. Does this make sense? So if I start with 33 moles of this stuff, how many moles of AlCl3 would I have? Well, for every 6 KCl, I have 2 AlCl3. Okay? So again, for every 6 KCl, I have 2 AlCl3. So I'm going to lose about a third of those, and that means 11 is going to be a reasonable answer to this question. Again, these are mole-to-mole calculations. They're one step. All you need to look at is the balanced equation to get the mole ratio. Sadly, it gets a little bit more complicated when we go between different units. Okay, so mole-to-mole ratios, that's a nice one-step process. But another common type of calculation is when I go from moles of a given substance to grams of another substance. And that could easily be grams of a given substance to moles of another substance. We call these mole-to-mass calculations. But again, I could flip that and make that a mass-to-mole calculation. So Marvin the mole and a scale. This represents moles, good old Marvin. This represents mass because we weigh things on a scale in order to get the mass. So what do I need to know in order to complete mole-to-mass calculations or mass-to-mole calculations? It gets a little bit more complicated. Again, this isn't written down in your note packets, but it might help you. These are two-step processes. Okay, so it gets definitely, like I said, more complicated. What do I need to know? Again, need to know my mole ratio. That hasn't changed. But the other thing I need to know then is the molar mass and how to find the molar mass of substances. So again, I'm bringing back a lot of what we did in the last unit. So let's look at the more complicated mole-to-mass or mass-to-mole calculations. Example, pretend you have the balanced equation below. How many grams of CO2 would be produced by burning 2 moles of C5H12 in excess oxygen? All right, so let's underline the important information. How many grams of CO2? That is what I want. If I burn 2 moles of C5H12, that is what I'm given. Again, this follow-up question about the mole ratio between those two amounts, it's never going to be there. But we have to think about the connection between what I want and what I'm given. All right, let's fill in our mole ratio right off the bat, since that's kind of the easiest thing to do. So if I compare CO2 and C5H12, I have a 5-to-1 ratio between those two numbers. I'm going to need to use that at some point. Again, these are two-step processes, so they get a little bit more complicated. All right, let's start with what I'm given. That's always what I do. So I'm going to put 2 moles of C5H12. That's the first thing. Now, I'm going to need to somehow get to my final answer, which is grams all the way over here of CO2. So I have a two-step process to get to there. How am I going to do it? All right, now here's why these questions are a little bit more complicated. To go from moles of one substance to moles of something else, that's when I use my mole ratio. So I'm going to use my 5:1 ratio first. All right, and that's moles of CO2 and moles of C5H12. Why did I need to do that first? Because I want my moles of C5H12 to cancel with moles of C5H12. Okay, so again, we have to think through this process. Now, by just doing that first step, I have moles of CO2. Now I need to somehow get that to grams. Luckily, I know how to convert between moles and grams. I need to use molar mass. So I need to add up the molar mass of what I want. CO2. So look at your periodic table, CO2, add that together. The molar mass of 1 mole of CO2 is 44 grams in 1 mole of CO2. So that's what I do second. Why did I need to do that? So I could get from moles of CO2 to grams of CO2. So now I can plug that in my calculator. What is 2 times 5 divided by 1 times 44 divided by 1? Well, when we do that, I don't even really need a calculator. That is 440 grams of CO2. So that is one possible conversion. And all I had to do was just follow some logical steps. All right, so let's try a second one. Example, pretend you have the balanced equation below. How many moles of K2CO3 would you need to make 0.25 grams of KCl? Let's underline the important information. How many moles of K2CO3 would you need? That's what I want. 0.25 grams of KCl, that's what I'm given. All right, so again, this follow-up question will never be there, but we have to look at the relationship between what I want and what I'm given. So when I look at my nice balanced equation, what do I see? I see I have 3 of these, I have 6 of those. So that is a 3 to 6 ratio. Again, you could have simplified that down to a 1 to 2. Either way, you would have gotten the same result. So let's plug this in. Okay, this is a two-step process because I have 2 different units, moles and grams. So let's put what I'm given, 0.25 grams of KCl. And what do I want? All the way on the opposite side here, I want moles of K2CO3. Somehow I have to string together some conversions to get to this. So unlike the first one, I do not use my mole ratio first because my mole ratio is in moles and I'm not given something in moles to start with. So the first thing I need is molar mass. I can go from grams of something to moles of something. So I need to add up my molar mass for my substances. I need to find my molar mass of KCl. So add that up from the periodic table and I get 74.55. And that's grams of KCl in 1 mole of KCl. Very important. Okay? Now that I have moles of KCl, I can convert from moles of one thing to moles of something else using my mole ratio. And so remember, my mole ratio was 3 moles of K2CO3 to 6 moles of KCl. So why did I do any of this? Well, I need to go from grams of KCl. My grams of KCl need to cancel. Moles of KCl can cancel. So when I multiply all of this out, 0.25 times 1 divided by 74.55 multiplied by 3 divided by 6, this is what I get. 0.0017 moles of K2CO3. All right, and so again, those are mole to mass and mass to mole calculations. So what makes that a little bit more difficult is that they are two-step processes, and I actually have to think, how do I convert from one thing to another? And so again, if you need to review this, you need to go back and watch this a couple of times just to see the pattern. Feel free, but that is, again, sort of how to convert from mole to mass or mass to mole. So there are two variations of this second type of conversion. And again, that's what makes it a little bit more complicated whenever people sort of have problems. It tends to be with this type of process. Again, questions, make sure you ask tomorrow.